Hello everyone. In this video, I'm going to explain the concept of transmissibility ratio. There can be a little bit of background noise, background life, so I'm very sorry if that is a bit disturbing to you. Nonetheless, let us start the derivation of transmissibility ratio. Before I get straight into the business of what is transmissibility ratio, let us consider a physical scenario. Just imagine that there is a chamber in which I'm just going to place a mass. This is just an analogy, so forget about the details. Now what I'm actually going to do is I'm going to give a push to this mass inside this chamber. So I'm just going to apply a force to this mass. Now what is the magnitude of the force that is applied to the mass? How do you express that? How do you give that expression? Very simple. The magnitude of the force that is applied to this mass is given by the expression F is equal to ma. It is force is mass times acceleration. That's it. It's very simple. Now, let us say that we have this as the foundation. Let us say that this is a wall. Now, the question here is, in this particular physical scenario, do you think this wall is going to offer any reaction? Definitely not. This wall is not going to offer any reaction. So I will just say there will be no reaction that is offered by the wall. The only force that is acting on the mass is F is equal to ma, and this mass, because of inertia, gives the same force back to the person, and that is also given by ma. So for every action, according to Newton's third law, there is an equal and opposite reaction. Perfectly fine. Now let us consider the second physical scenario. The second physical scenario, you are going to consider the same chamber and you are going to have the same mass m. But this time, what you are actually going to do, you are going to give the force, but just imagine you also have got molecules of fluid inside. So that is represented by this little green circles. That represents the molecules of fluid that is present inside this chamber. The question here is, if you apply a force, what is the physical scenario this time? Will there be any reaction offered by the wall? Well, when you apply a force of magnitude, let us say that you are applying a force, you have to say that the force is divided into two. Now the first force is, there will definitely be ma, which is the mass times acceleration, because this mass is going to accelerate, but at the same time there will be a second force, and that is this offered by this green little guys. They are going to offer a second force. Let us call this a drag force. So the force that you are going to apply actually accelerates the mass, and also you have to overcome the drag resistance that is offered by the green guys. So the resistance that is offered by this, the resistance that is experienced by this person will be ma, which is mass times acceleration, and also there is also going to be another resistance which is given by the drag force. The green little guys, they are going to offer a resistance. But also remember, this time the foundation is going to offer the reaction. The question here is, what is the magnitude of the reaction that this wall, when I say the word foundation, I'm talking about the wall. What is the magnitude of the reaction that this wall is going to offer? The magnitude of the reaction this wall is going to offer is given by the expression F drag, which means this wall is going to offer the drag resistance. Why? Well, the inertia resistance that is offered only by the mass. These little green guys have got nothing to do with ma. So when you are pushing this mass, you are actually pushing against the pressure force. So clearly, obviously, it's quite intuitive that this foundation will offer the reaction, that is the drag reaction this foundation is going to offer. If you want an even more intuitive feel of how that is going to work, so let us try this way. Get rid of this foundation and put yourself in this position. Just imagine you are here, right? You are here, and let us think of this way. When you are here And when a person is pushing against this mass, you are not going to feel MA, but nonetheless, these little guys will be pushed against you and you will be offering a reaction back. So that is quite an intuitive concept. Now, we know what is case 1. There will be no reaction by the wall. In case 2, definitely the reaction offered by the wall is equal to the drag force. Let us move to this case 3. And of course, we are going to build on case 2 to how to understand case 3. It's very simple. Now, I think case 3 will become very clear. Let's say that you have this mass. That's right. And this mass is supported by a spring and also a damper. This time, when you are going to apply an action force, the action force is divided into 3. The first one is mass times acceleration. That's right. The second force is going to be the spring force, which is offered by the Hooke's law, which is k into x, the displacement of the mass. And the third one is going to be the damping force, which is given by the expression c into dx over dt. Out of these 3 forces, for obvious reasons, the MA will not be offered by the foundation. So this is our foundation here. Definitely this MA, that resistance, that force will not be transmitted to the foundation. Keep that in mind. So when you are applying a force on top of this mass, when you are applying a force, not all the force gets transmitted to the foundation, right? The force that is actually transmitted, the forces that are actually transmitted to the foundation will be only 2. One is the damping force and the second one is the spring force. Only these 2 forces will be transmitted to the foundation and MA will not be transmitted to the foundation. That is how the suspension system actually works, and that is how the vibration isolation actually works. So the MA will not be transmitted to the foundation. So that is quite interesting. So you are sort of actually preventing the foundation from getting damaged. It will not be transmitted to the foundation. So the 2 forces that are transmitted to the foundation are the first force, it's going to be the damping force, which is given by the expression c into dx over dt, which is velocity, and the next force will be the spring force. It is k into x. Right, in the next page, we are going to simplify this even further. Let us build on the mathematics. Now, this is a physical scenario, guys. So now the physical scenario is clearly established. Now the mathematics is going to take over. Let us do the mathematics now. All right. Now, the force that is transmitted to the foundation is given by the damping force, which is given by the damping coefficient into velocity. Velocity is first derivative of the displacement, and the spring force, which is given by Hooke's law, which is k into x. You have to check my video to find the expression for the response for the forced vibration. I'm just going to write that expression. X of t is equal to, it's x naught divided by square root of 2 zeta r the whole square plus 1 minus r squared the whole square, 1 minus r squared the whole square into sine omega t minus phi. You want to know what is what in this expression? Please go back and watch the response for the forced vibration. I have derived the governing differential equation for the forced vibratory system, and also I have solved the governing differential equation to get this particular response that is given by this red box, given in this red box. That's right. So this is the response. Now what I'm actually going to do is I'm going to take this. Mathematics is just like moving objects, right? So I'm going to move this fellow over here. So instead of x, I'm just going to move this guy over here, and I'm going to find out what is x dot, which is dx over dt. And once I find dx over dt, I can move this dx over dt here. So that's what I'm going to do. So let's try this. So first, let us find out what is dx over dt. So dx over dt is very simple. It is, if you differentiate sine, it becomes cos, right? Okay, we will do that. Even before that, just for simplification, I will call this, everything is a constant here, right? X naught, that's a constant. Damping factor is a constant. R is omega by omega, and that's going to be a constant. So everything is a constant. I will call this as alpha. So if you want to find out, so this expression is simply alpha into sine omega t minus phi. So that is very simple now. If you differentiate this, this becomes alpha. If you differentiate sine, it becomes cos. Of course, you have omega cos omega t minus phi, and you have to differentiate omega t again. That brings omega outside this expression. That is dx over dt. Now you have to take this dx over dt and put it in this expression. So let us see what comes out of this expression. So Ft, that is the force that is transmitted to the foundation, is now given by the expression. It is C into, what is dx over dt? It is alpha into omega into cos, that's right, cos omega t minus phi plus k into x. What is x? It's alpha into sine omega t minus phi. So that is equal to, now in the next step what I'm actually going to do is I'm going to pull this alpha common outside. So I'll be getting alpha into c into omega into cos omega t minus phi, that's right, plus k into sine omega t minus phi, that's right, fine. Now in the next step what I'm going to do is I'm going to call, see, this is just a number, c into omega, it's damping coefficient into angular velocity, that's just a number. You can represent a number by a product of two numbers, which is capital X into sine. Already phi is used, so I'll use the notation psi. And again, k, stiffness is just a number, it's just a number. Any number can be represented by the product of two numbers. Again, I'm using capital X into cos psi. Now I can find out what is x. Very simple. If I square and add these two terms, I'll be getting x squared. So if I square and add these two terms, I'll be getting simply x squared, because sine squared psi plus cos squared psi is 1. You pull the x squared common outside. Okay? And what is this first term square? It's c square omega square. What is the second term square? It's k square. So now I know what is x. Now I know what is x. So keep this at the back of your mind, guys. I'm going to simplify this x a little bit, and I'm going to come back, revisit this expression. Okay? I'm going to do this, but let me simplify this x further. So in the next step, I'm going to simplify just this expression x. X is equal to root over c square omega square plus k square. That's right. It is equal to, pull this k common outside. So you will be getting, it's going to be 1 plus c square omega square by k square, because I'm pulling the k's outside of the root, k squared outside of the root. If I take k squared outside of the root, I have to multiply and divide by k squared for this term, right? I have to multiply and divide by k squared, so I do no damage to the equation. So I can pull k squared common outside. So in the next step, it's going to be k into square root of 1 plus c square omega square divided by, you know what is k squared? Omega n is root of k by m. So omega n is root of k over m. Simplify for k, it's omega square, omega n square into m. So that's what k is. So what is k square? It's omega n squared into m, the whole square. That's right. So go ahead and plug that value here in the denominator. So you're going to get omega n square into m, the whole square. So I'll write that as omega n square into m into omega n square into m, and simply I'll call this omega square by omega n squared as r squared. I can call that way, right? As r squared. So in the next step, I'm going to say it's k into square root of 1 plus c square into r square divided by omega n square into m square. Now what I'm going to do is I'm going to multiply by 2 square and divide by 2 square. Multiply by 2 square and divide by 2 square. So I'm not going to do any damage to this equation. So if I do that, in the next step, it's going to be k into root over It's going to be 1 plus 2 square into c square into r square divided by, it can be written as, what is 2 into m into omega n? 2 into m into omega n is c suffix c, which is critical damping coefficient, the whole square. That's right. And what do you say c by cc? C by cc is damping coefficients, zeta. So this can be further written as k into root over 1 plus 2 square into zeta square, because what is zeta? C by cc. So c by cc the whole square, that is zeta square into r square. And that can be nicely written as k, simply, very simple, last step, k into root of 1 plus 2 into zeta into r the whole square. I'm sorry I'm making this a little bit cluttered, definitely not with the intention of making it look cluttered. Anyway, so that is the final expression. And what is this expression for? X. So all I'm going to do is go back to this equation. I can pull x common outside, and instead of x, I'm going to plug this value. Shall we do this in the next step? That's right. So Ft, the force that is transmitted to the foundation, I'm going to plug x common outside. If I do that, you look here, I'll be getting sin psi into cos omega t minus phi plus, what is that we're going to get? Cos psi into sin omega t minus phi. Cos psi into sin omega t minus phi. That's right. So in the next step, it can be written as, I'm going to plug the value of x we have derived. We have taken some effort to derive what is x. I'm going to plug that value. This is of the form sin A cos B plus cos A sin B, and that is sin A minus B. In mathematics, it's like moving objects. Instead of A, excuse me, you have omega t minus phi sin A minus B, which is sine. That's right. So what is x, by the way? It's very simple. X, we have already derived what is x. It's k into. I think we are continuously missing one term here. For the transmissibility ratio, we are missing this alpha. We missed this alpha. We shouldn't be missing. So please carry that term with you. So it's going to be alpha into what is x. Now we will plug that value. It is k into root of 1 plus 2 zeta r the whole square into sine omega t minus phi minus sine. That's right. Finally, we are going to plug the value of alpha. What is alpha? Well, this is our alpha. The one that is shown by this yellow blob here, this one, that is alpha. It is x naught over square root of, that's right, it is x naught over square root of 1, okay, it is x naught over square root of 2 zeta r the whole square, 2 zeta r the whole square plus 1 minus r square the whole square into k into square root of 1 plus 2 zeta r the whole square into sine omega t minus phi minus sine. That is correct. So is there anything else? Okay, fine. It's square root of 1 plus 2 zeta r the whole square divided by, okay, fine. Now, what is x naught into k? We have this equation. Well, x naught, you have to go back to the solution for the force vibration to understand what is x naught. I have explained in that video. But anyway, x naught here stands for the static deflection equivalent to the applied force. So what is stiffness? Stiffness is, I'll use a different color. Stiffness is force by deflection, static deflection. So x naught into k is given by simply the force that you are applying. So it's just another way of representing, that's all. So you can say this is F. So in the next step, the final expression for the force that is transmitted to the foundation is given by, it is simply capital F into root of 1 plus 2 zeta r the whole square. Root of 1 plus 2 zeta r the whole square divided by square root of 2 zeta r the whole square plus 1 minus r square the whole square into sine omega t minus phi minus psi. Now the question here is, I'm not just interested in just finding the transmitted force. I'm interested in finding the maximum force that is transmitted. For that, this term should be 1. So the final expression for the force that is transmitted is given by capital F into square root of 1 plus 2 zeta r the whole square divided by square root of 2 zeta r the whole square plus 1 minus r square the whole square. That is the maximum force that is transmitted to the foundation. So it's going to be Ft maximum. And if you just bring this guy here to the denominator, the expression that you are going to get will be Ft by F. So it's Ft, the maximum force that is transmitted to the foundation. It's the ratio of the maximum force that is transmitted to the foundation to the force that you're actually applying is given by this expression. And that is our transmissibility ratio. So TR is an acronym for transmissibility ratio, which is the ratio of the force that is transmitted to the foundation to the force that you are actually applying on the object. So you can simulate this in MATLAB. In the next class, we will try to simulate this, understand the physical meaning and the significance of the force that is transmitted to the foundation, and what is the speed at which you have to run the machine or the motor to make sure that the foundation is not so damaged. We can simulate this in MATLAB. We can delve deeper into the subject matter. Thank you all for your patience. Thank you so much.